We're moving on to the next section of the class. The last section was visual image interpretation, where you have an unprocessed image, you have some kind of human interpreter, and they create a derived product. We're now moving on to digital image processing, where we're automatically processing images to derive something useful. I've got automatically there in quotes because there's usually some supervision, or in fact, a lot of supervision of the computer algorithms that take the unprocessed image and create a derived product. So we're going to talk about three aspects of digital image processing. One of them will be image correction. So that's sort of a pre-processing step. So all airborne or satellite images have geometric and radiometric errors that must be corrected prior to image analysis. It's rare that you can just use an image straight out of the source material. Then we're going to talk about image enhancement, so techniques that we use to increase visual distinctions between image features, and also to create new images that summarize aspects of an image that aren't directly available from the original images. And so here I'm thinking about texture. We'll talk about how to bring out various aspects of texture in a way that we can directly process them. These can also be used to improve your visual image interpretation. And then image classification. So using quantitative methods to identify different classes of features or land cover in an automated manner. And so generally that involves the creation of land use or land cover maps. This is probably still the main objective of most remote sensing applications, creating some kind of cover map. So let's talk about image correction. Images may have visible defects or quantitative biases that are not immediately visible, okay? So you might need to restore image, bad data in an image. You need to very often rectify images, that is, take the original image and give it geometric coordinates, and just try to correct any errors that are in the image. At this time, many images are supplied with these corrections already made, but it's useful to know what these corrections are, how they're made, and which ones are needed, so that you can double check images when you know what corrections have been made to them. More highly processed data products are most appropriate for non-specialists, but for certain types of data, those extra processing steps are expensive. And here I'm thinking about particularly high spatial resolution images that are commercially provided. They will provide you a base data product at one cost, and then but for higher levels of geometric correction or removal of image errors, they may charge you a higher price. And therefore, it's good to understand what degree of correction is necessary so you don't buy something that you don't need, and have an idea of what's involved so you may decide that you want to do the corrections yourself. So let's talk first about a radiometric correction. Radiometric correction means actually changing the values of individual pixels in an image. One problem that radiometric correction addresses is sensor-generated noise. So that's noise that's generated by a sensor. It really can be either a malfunction, or it can just be, for instance, noise that that is an inherent part of the data collection process. And so those that noise can either mask features or just degrade the radiometric information, so just by making it noisier. There are three main types of sensor malfunctions that we'll talk about. Systematic striping or banding. These are lines of pixels with spurious digital numbers. This is a systematic error caused by detector drift over time. We'll talk about line drop, lines of pixels with missing digital numbers. This could be systematic, but it's usually random, and it's caused by sensor malfunction. And then bit errors, spiky or salt and pepper variations from pixel to pixel that occur in a random fashion. So systematic striping or banding, this is caused by detector drift. So it's a line of pixels with spurious digital numbers, the values in the pixels. These types of problems were most common in data from, or are most common in data from older sensors, such as Landsat MSS. We'll talk about this as we go on. Landsat, the MSS is the multispectral scanner. That was the first useful sensor launched on the Landsat series of satellites, and so the MSS record goes back to 1972. And it's got a lot of problems, to be honest. It doesn't really have all the spectral bands you'd like to have. And it does have this banding problem if not properly corrected. But it's really the only data source of the kind that goes back to 1972. So people still have to utilize MSS if they want to go back that far. So there you can see there's a striping effect in that image. MSS is a cross-track scanner, but rather than just making one observation every time it scans left to right or right to left, it's actually making 6 observations. There's like you can imagine it as a paintbrush going left and right, or a whisk broom, as we say. But inside the brush or inside the broom, there are 6 pixels that are being scanned simultaneously. Over time, data in the 6th line, those sensors changed their calibration. They became less sensitive to light than the other 5 lines. And that's why you get this banding or striping effect. So the data are good, but the calibration is different than for those other 5 lines. So what do? We can apply some algorithms to adjust the incorrect brightness values. And you got to assume, or you have to have errors that are systematic to achieve a good correction. So what they do is, for every detector in a given band, they generate a histogram. Okay, and if you look down there in the bottom, you can see, you've got 5 histograms there, and one of them you have higher values than this particular one. So you know that because these are, there's a certain minimum scale to variation, right? So values in one line should pretty much match values in the next line. And so that histogram, that difference in the mean value, must mean that it's detecting in a different way. Okay, that's the difference in calibration. For basically the same object on the ground, you're getting different values. okay? And so what you can do is figure out the difference between the mean of the bad band and the mean of the adjacent bands, and then shift those values by the difference. So then you wind up with histograms that are all of the, with the same mean. So here's a before and after image of removal of the striping or banding, and you can see you get better results once they're removed. If you look in the water, you can see there's some residual effect, but it is much better. The water being the dark areas here. Line drop. Line drop is lines of pixels with missing digital numbers. It can be systematic, but it's usually random, and it's caused by a sensor malfunction. So there are system errors, which mean that data just wasn't correctly stored. That data is essentially missing. Normally, that's corrected by replacing the line with data from the pixel values in the line above or below, or possibly with the average of the pixel values from above or below. Again, you think, how could something like this happen? You got to remember, going back to 1972, people are watching like black and white televisions. The technology is completely different. And basically, these people were winging it on sensor design. One thing that is interesting is that the early satellites, they didn't have solid state memory. They didn't have memory chips. They actually recorded things onto tape recorders and then played the information back when they got to the point where they could downlink to satellite dishes. So you could just have a bad section of tape, and sometimes the data came in so quickly that the tape couldn't catch up with recording the data. So, you just got to remember, very primitive technology, but the next best sensor was put onto the Landsat series in 1984. So you got 12 years of time where you would like to have observations, and MSS is what you got, and these are the kind of problems that arise. A much later problem is the problem that occurred with something called the scan line corrector in Landsat 7. And Landsat 7 collected good data for 3 or 4 years, and then problems occurred. If you look at the images to the top right where it says with and without SLC, basically as the satellite is moving forward, okay? If you were just scanning back and forth, right, you're scanning left to right, but during that time, the satellite is moving forward. And so what you would wind up is with that pattern that's labeled without SLC, okay? What the SLC does is it moves the field of view, the area you're observing on the ground, backwards with a mirror. So the field of view relative to the satellite is moving backwards, but the satellite is moving forward, okay? So it corrects for this, the effect of the sensor moving forward. And you can see there down on the bottom right, you have a reverse scan from right to left, and then you're moving forward and you have this forward scan, but you wind up with a gap. And on the left, we have just a portion of the Landsat 7 image, and you can see where the data gaps are. And you can kind of imagine that if all of these were sort of compressed, sort of rotated to the left, that that data would be, would appear correct. There would be gaps, but they would at least be parallel to the direction of forward movement. So how do you fix that data? Basically, there's no good solution to this. You are missing data. Some people have filled in missing values with an average of the scan line above and below. Unfortunately, these scan lines, the missing data, it's too wide. You're missing too much data to just use a single pixel to fill it in. So that's not very good. Alternatively, you can simply replace the missing data with data from the preceding scan line. The spatial location of the errors will vary between acquisitions. So you could take missing values from an adjacent acquisition cycle. So sort of basically composite, we'll talk about compositing images together to get a single good image. So, I mean, Landsat 7, you want to do what you can with the data. So there have been multiple attempts to come up with a decent data product. Fortunately, now if you look at the sequence, and we'll talk about this when we talk about different optical systems, Landsat 7 collected data for 3 or 4 years, and then it ran into this problem. Landsat 6 was lost. The rocket carrying it fell into the ocean. Landsat 5, first of all, you got to remember these systems are only designed to collect data for about 5 years. But you never know. And Landsat 5 collected data for 25 years. So as a consequence, Landsat 7 became, and the loss of Landsat 6 became less important because Landsat 5 managed to have this incredibly long, useful lifetime. Okay, so bit errors. So these are errors on the pixel level. Okay, so they're like spiky. You see little points, sometimes called salt and pepper, just sort of these, if you just threw salt and pepper out on a table and they were just kind of randomly mixed, some people say it looks like an image has been shot with a shotgun. How do you fix the data? Well, we'll talk about spatial filtering. And this is one application of spatial filtering. You can go over the entire image and basically average all those values within a small area, like a 3x3 window, and fix the bit errors by just replacing bad values with the average of the surrounding pixels. And so at the top is a large image with bit errors, and then here are 2 subsets toward the bottom, and in this case these are dark values, and again they've just been replaced on the right with the average of the values in the adjacent area. And so there's a particularly bad image on the left, filled with bit errors, and so there's the before and here's the after. And again, a lot of the things we've talked about, the basis of the approach is that within small areas, you tend to have the same kind of cover, and so the same kind of digital values in your image, and therefore you can assume that adjacent pixels can be sort of substituted for each other, or their average can be substituted for each other.